time is relative, okay? Now, but he made it even stranger.
Is a TV that does it all too much to ask for? Curry's expert Lewis doesn't think so. The Hisense U7K Mini LED is a great all-rounder. The brightness, the lifelike color.
Because he said, well, not only does time depend on emotion, but time depends upon where you are, literally. If you're in a gravitational field, which we all are, our clocks tick at a different rate than if we're not in a gravitational field. And this was extremely strange, but it meant you could measure. And if you click once, okay, and then click again. Okay, this is where I used to have my office. This is the Jefferson Physics Lab at Harvard. And if you look at there, you see a little shack on the top. And that was actually built for this experiment by Robert Pound and his assistant Rebka in the I think it was early 1960s. They did an amazing experiment. If you just click once and then click one more time, actually, and then click one more time, we'll get all of them. Okay. What Pound realized was, well, if he put a clock on top of the Harvard Physics Building and had a clock on the bottom of the Harvard Physics Building, they're separated. The one at the top of the Harvard Physics Building is farther away from the center of the Earth than the one at the bottom. So they're experiencing different gravitational fields by a very small amount. Although this is unintelligible here, they differ by the gravitational, the effect that Einstein suggested would be there was 1 part in 10 to the 15th. A millionth of a billion. So when one clock ticked 1 second, the other would tick 1 second, but off by a millionth of a second. You never think you'd be able to measure that, but they did, because they were able to send a careful, we call it a laser nowadays, up from the basement, and lasers are like clocks because the light has a frequency. And well, in this case, it was actually a light that came from a radioactive decay, a very specific frequency, and a decay of iron. And in those days, the way they communicated was by telephone from the top of the physics building to the bottom, because there was no internet. And what happened was they were able to show that the frequency of light that was emitted by the decay of iron in the bottom, when it got to the top, had changed by exactly the amount that Einstein predicted. And similarly, they did it in the other direction. And I could go into that. But it was an amazing discovery, because it meant that suddenly time was not universal in any sense. If you're at a higher altitude, your clocks are different, and if you're at lower altitude, then your clocks are different as well. And the fact that became an aspect of general relativity which changed everything, because it put time and space on the same footing. And that meant time was even stranger. Because if space and time, which are the fundamental variables of general relativity, are the same, how come I can come to London and back and do a round trip in space, but not a round trip in time? Why can't I go to the future and back? Or to the past and back? Because if space and time are the same, I should be able to do that. And in fact, general relativity says you should be able to do it. Because general relativity is really simple. It's a simple equation. There's left-hand side equals right-hand side. Okay? Everyone gets that part? Okay. And the left-hand side is the geometry of space. And the right-hand side is the energy and momentum of the stuff in space. Now, if I want to create a geometry of space and time that allows time travel, I can, as long as I can write it down mathematically, then there must be a kind of energy that I can write down mathematically on the right-hand side that will produce that kind of space. Because space and time are determined by the configuration of matter and energy within. So mathematically, I can always write down a space where there's time travel. And then it implies what kind of energy I need to produce that. Now the key question is, can you produce that kind of energy?
I'm taking fire!
Okay, and the answer is we don't know.
Reloading.
It's one of the first we don't know questions. And as I said in my book, I don't know is the most important 3 words in science, and it should be the most important 3 words in society. Much of the current culture wars and everything else would disappear if people weren't so certain that they know the truth before you even ask the questions. But we don't know. And time travel is still therefore an open question. When I wrote my book, The Physics of Star Trek, my late friend Stephen Hawking wrote the foreword for it. And he had said that time travel was impossible. And he gave a very good argument. He said if time travel were possible, we'd already be inundated by tourists from the future. You know, in fact, he actually even held a party and invited time travelers. Okay? No one showed up. Okay? So he said time travel was impossible. And I countered him, however, by saying that they all went back to the 1960s and no one noticed. And so he had to change his mind. But what is amazing to me is it's an open question at the forefront of science. We don't know that time travel is impossible. And if it is possible, you know a host of paradoxes result. And that's why most physicists hope that time travel is impossible in a sense. But as I've said many times, the universe doesn't exist to make us happy. And maybe time travel is possible. And we have to change our notions, maybe even of cause and effect. Because it's nature that gets to determine what's sensible, not us. Okay? Now, when I talk to people about this and I see their eyes glaze over, as some of yours are, I want to point out that you know, people often ask, since the science I do, and not like some of the other science you're going to hear about, I'm very proud of the fact that the science I do has absolutely no practical significance whatsoever. Okay? Because it's a unfortunate aspect in some sense in my mind that science produces technology. It's not unfortunate. It allows us all to be here and many of us be alive when we wouldn't be alive otherwise. But suddenly, because science produces technology, for many people science becomes equivalent to technology. And then people say, of what use is this? Right? If it doesn't produce a faster car, a better toaster, why worry about weird aspects of clocks in space or the beginning of the universe or the end? And the point is that the real beauty of science, the magic of reality, as a good friend of mine in the back put it once, is the fact that it's the ideas that come from science. That's what makes it so beautiful. The fact that it changes our perspective of our place in the cosmos. And so that's why we should celebrate, because science keeps opening our mind by showing us what we don't know. And by provoking questions, not answers. By provoking questions, and that's the key aspect of science, which I may get to in a bit. But for those people who nevertheless are of a practical bent, I should point out, go to the next slide, that this abstract aspect of general relativity, that clocks change when they're high up and down, every one of you, I certainly used it today to get here. Actually, my taxi driver did, but same thing. Okay, every one of you uses a GPS, usually on a daily basis. Well, the satellites and the GPS are they're moving very fast, and because they're moving very fast to the ground, the way a GPS works is quite simple. You have a bunch of satellites with atomic clocks. You receive the signals from 2 or 3 of them, and you find out how long it took for the signal to go to you from the clock. And time travel tells us light travel. Light, you work out by 3 clocks, you can triangulate where you are by finding out how long it took for each of those signals to get to you. But that requires that all the clocks be synchronized. But they're moving because they're in orbit. So their clocks are traveling, in fact, slower than a clock on the ground, at least as measured on the ground. But it's even worse. They're at an altitude of maybe 12,000, 14,000, 24,000 miles above the Earth's surface, so they're at a different place than gravitational field. You can calculate that because of the effects of general relativity, the clocks will change by about 43 microseconds within a few hours because of the fact compared to a clock on the ground. And if you work out how fast light travels, within about 10 minutes, you'd be a kilometer wrong. If we didn't build into this and take into account the fact that these clocks are traveling at a different rate, or ticking at a different rate than the clock on the ground. So every one of you was able to use GPS and not get lost in 10 minutes a kilometer away from where you thought you'd be, precisely because we take into account the fact that time does change. So that abstract thing actually is about as useful as anything technologically, because it allows us to get around for now and then. So, but we still don't know the key questions like, will time end? How did time begin? And can we go back and forward in time? Those are things I talk about in the book, and talk about those open questions. But time is perhaps the most personal and most direct. I begin my book with it because time, for all of us, is perhaps the most personal thing we experience, the tragedy of time. the tragedy that we're all moving forward in the future and can't go back to either correct our errors or relive them, depending upon our mood. Next slide. I don't know if I ended. The thing about black holes. These, by the way, are called Penrose diagrams after Roger Penrose, who invented them. It's a way of thinking about the future and the past. And I don't want to go into explaining it, but what's really neat, one of the crazy things about black holes, and we don't know a lot about what happens inside black holes. We'd like to find out. But one of the strange things is, this is the future. We call this the light cone, because nothing can travel faster than light. So, and in this frame of reference, light travels at 45 degrees. So this is your future. Everything you can ever see will be in that light cone. And what's really weird is when you go inside of a black hole, all the light cones start pointing directly at the singularity at the center. And that means space becomes like time. Because no matter what you do, space always moves. No matter what you put, and you try and put your gas on, you're in a car, you're trying to go that way, you always move inexorably towards a singularity. And so space becomes like time, and it turns out time becomes like space. So the two things flip when you're inside a black hole, and that is remarkable. One of the very strange things about black holes, because this is the most extreme place that gravity is important. And of course, the key question is, what happens here? Because space ends, does time end? Or does it go to a different universe? All of these are open questions at the forefront of physics, and one of the things that many people like me have been paid to worry about. Okay, let's go to the next topic, which is much closer to the many of you, and so some of the other things you're going to hear about. I want to talk about life. Okay, next. I think I have a quote. Oh yeah, from I think Sartre. Everything has been figured out except how to live. And that certainly seems to be the case more and more every day. Let's just go to the next slide. There's so many aspects of life. And people may wonder why a physicist would talk about life. There's a long history of physicists talking about life. I mean, the first one is really Carl Sagan. He did it in terms of the apple pie. He said, if you wish to make an apple pie from scratch, you must first invent the universe.